Welcome to two approaches to cleaning, with microbubbles generated by fluidic oscillation, with and without plasma injection, and optimization of scheduling integrating cleaning. Cleaning problems cost both time and money. Up to 50% of production, particularly in pharmaceutical, is lost to cleaning, and that's a huge impact both on time and on products being able to be delivered to the customer, in addition to the cost, of course. And pharma, ag, fine chems and food all have these issues. One of the other issues is the unpredictability of cleaning times, and so messing up a schedule, and the significant amounts of waste that cleaning produces. The other issue is the time and number of samples needed, and obviously that costs time and money and causes unpredictability, and is a significant issue we need to deal with. And things like staining and bacterial contamination can also add further complexity. So as we said, this is going to look at two approaches with microbubbles and scheduling to reduce the cleaning time by introducing and integrating cleaning into the optimization. The fluidic oscillators make microbubbles, and you can see here with the same diffuser with and without the fluidic oscillator, you can see the difference in making monodispersed bubbles, very small microbubbles that are generated. When the team were working on both lab and pilot scale algae screening using microbubbles, they found that all the surfaces were squeaky clean, and that led us to understand that microbubbles could play a huge part in cleaning of surfaces. So further work was done to look at the impact on biofilms, and you can see the setup here with the hanging glass surfaces with a microbubble plume. And here in the confocal micrographs you can see with 0.1% surfactant the impact of the microbubbles for the cleaning time and just how good it is, with 90% removal in 7 minutes. But with simulant material, 2% simulated enhanced microbubbles, you can see here greater than 90% removal in 3 minutes, which is significantly better than the best literature results. And here under the SEMs you can look at the biofilm reduction or removal with the 2% simulated microbubbles, and these are at 1000 and 2000 magnification, and the difference between the untreated biofilm and the treated biofilm, and again you can see the significant improvement. So plasma activated microbubbles are the next thing that was tried, and you can see the new injector with the diffuser and the electrode, and it's submerged in liquid and creates plasma activated microbubbles. And the key thing here is it creates hydroxyl radicals at the interface. And here is the setup for a pilot trial at United Utilities wastewater treatment plant, and the lance was submerged and carried out at different depths, and oscillation was demonstrated, the ability to secure superior control of the bubble size at all the different depths, and here are some of the results. So if you look on the top left graph, you can see the significant improvement of removing colony forming units over time. What that top left graph doesn't show is just the logarithmic benefit of 5 log disinfectant achieved, and if you look at the bottom right graph that is a logarithmic scale, you can see that significant improvement there. And the old lance versus the new lance saves time, but also draws an awful lot less energy with 5 watts rather than 130 watts. So some really good results there to show the benefits of micro bubbles with plasma activated lamps. So that the microbubbles show that we can make a huge difference on cleaning times and cleaning quality, which can give improved accuracy and also reduce the time of analytical work that needs to be done, because you can be more sure of the cleaning. So when you take that into account, and you take into account the different factors that can impact cleaning, you can put that into an optimization system. And here are a number of the factors that are important in that optimization. Clearly, the quality levels that you need to clean between, or the residual impurity levels that you need to clean between products, can make a huge difference. And that might be, 750 ppm between the products, or it might be less than 1 ppm between products, and clearly that can make a huge difference. Water solubility, or whether there's solvents there, the number of pieces of equipment and how difficult to clean that equipment is, the analytical method accuracy and the stability of the standards. From what I've seen, the analytical method might need to be accurate down to 0.1 parts per million, and often GC methods are only accurate to 3%, and so your standard analytical method that you use for your product quality is often not the same method that you need for cleaning. And the stability of standards can have a huge impact. In labs that I've managed, we've had standards that last less than a day and standards that are stable for years. So clearly that can make a huge difference, and often not considered when optimizations are done. And clearly staining levels of the formulation of the product's important, and obviously the bacterial contamination potential. And there's a big difference between when you expect bacterial contamination to happen or when you don't expect it, and it does happen. So it's really important that we are able to put some predictions together as where we would expect bacterial contamination. And obviously the design of equipment and pipework is important. So this is for plants that are already operating and products that are already operating, but also to be able to predict when new processes or new products are brought into a multi-product plant. Clearly, when you have a plant that's already operating with multiple products, you can also, in fact, put in known data between changeovers and add this to the model to improve the model prediction. So we don't have all the mechanistic understanding of all the different factors that are important in cleaning. So the optimization is a mixture, a surrogate model, where we have known data, we have the known data inserted, and where we don't have known data, we have pseudo parameters that are expert informed, that are programmed into the optimization. But also where we can use driving forces and mechanistic models, we've done so, and particularly physical property prediction techniques. So the algorithm uses a risk style approach and a risk level for programmatic cleaning, because in a sense, accuracy in terms of time is not important. It's the picking the right changeover and for the right scheduling is what is important, and the factors are weighted depending on expert input. So thank you. We've presented 2 ways of improving cleaning, one using microbubbles and one using a surrogate model and comparative risk-based model for optimizing the scheduling of products in multi-product plants, integrating the impact of cleaning. Thank you very much.